Okay, let's go to the next part of Kepler's laws here. And we'll start off at the same place we were before with the different equations we have for um, motion and orbital motion, centripetal and gravity. And this time we're going to do is we're going to talk about it in the way that the AP test likes to kind of introduce these kind of ratios and just get you to answer a question using it's this much larger, 2 times larger, or 4 times larger, or in that fashion. So let's take a look at the Earth Moon system again. And let's see if we can look at the kind of how Kepler was talking about. We can talk about these ratios. And once we find out about these ratios, we'll find out that the ratio is actually the same for any satellite in the Earth system. So we only have one natural satellite, right, which is the moon. And then we have many others, starting with Sputnik from Russia, to right now we have the International Space Station, to countless satellites from different companies that are up there broadcasting stuff and checking on you and see what's going on. So they all follow the same ratio. So let's check it out. Let's derive that a little bit. So first of all, what we have is the moon itself. And so where did my pen go? Where did my pen pencil go? Here it is. Here it is, the moon itself. So the moon is going around in this idea, this orbit, and we know, of course, like before, it is mv squared over r, and that is also equal to g times the mass of the Earth times the mass of the moon divided by r squared. And so this is exactly what we had done before, right? This idea about what the moon is doing. It's going that way with a velocity, but it's got a force that way. And so there you have it. So how do we get to the idea where it's the same ratio? Like, let's say I put a satellite, and this satellite will be 1/2 r, where this is r, this will be 1/2 r. And so what velocity will I put this satellite at? Just using percentages, just using instead of using a number to begin with, I want to just solve it in the way that AP test would ask you this question. So for this one, I'm going to solve the same thing. I'm going to say, yes, this one is also mv squared over r. And this is also g times m divided by r squared. So they're both the same equation, but some of the numbers are different, right? So true, some of the numbers are different. So let's do what we did before. This is the mass of the moon. This is also the mass of the moon, because we're talking about this guy right here. And they cancel. This is the radius, right there. And this one cancels one of them. So what we end up with, and what I'm going to do is I'm going to rearrange this so that I get all the things that are not constants on one side and all the things that are constants on the other side for this system. So I'm going to bring the r over here, because the r here, v squared of the moon, and radius for the moon is equal to capital G, which is a universal constant, times the mass of the Earth, capital M, mass of the Earth, capital M, and this is little m. These two are constants, right? These two are constants. Over here, the same thing applies, but this time I'm talking about the satellite, right? This is the satellite, S. And so the mass of the satellite here cancels. This one is also the mass of the satellite. And this radius of the satellite will cancel one of these. And so once again, if I put all the constants on one side and all the things that are not constant on the other side, I get v squared of the satellite and times r of the satellite equals gm. We'll check it out. That's a constant. That's a constant. G is obviously G. G is obviously a constant. It is the universal constant, so come on now. And then m is going to be the mass of the Earth, right? M is going to have a lot of arrows here, is going to be the mass of the Earth. So those two things are constant. So doesn't that mean that since this is equal to that, then I can say the velocity of the moon squared times the radius of the moon should be equal to the same ratio as the velocity of the satellite squared times the radius of the satellite. And yes, indeed, this is exactly what we're talking about with Kepler's law, saying that they fit these ratios that are involved. Okay, let's go ahead and continue with that idea. And let's now apply it to the, if I was to ask you the question, well, how much slower or faster should the satellite be if the radius is cut in half? Okay, so then what we have is the rule of ones. If you remember that, can I move this up higher? I think I can. So now we have the rule of ones. And remember, what we do is anything that's the same, we are going to put as a 1. So this is the velocity of the moon. It doesn't change. It's 1 squared. The radius, same as before, it's 1. Equals the velocity, the new velocity out is what I want to find. Because what I'm asking is, what will the velocity be at this distance, right? So the new velocity is what I want to find. So that's the velocity of the space station. And this is r, but the r is now 0.5. Right? And so if I do this and I solve for v, I'm going to end up getting basically v is equal to the square root of 1 divided by 0.5. And if I do that, I get the square root of 1 divided by 0.5. I get the square root of 2, which equals 1.41. And this is 1.41 times the velocity of the moon. Right? That's the idea. That's kind of how AP would ask you the question. It doesn't say how fast is the moon. It doesn't say how fast is the planet. It just says what, in comparing to the velocity of satellite A, what would the velocity of satellite B be? And so that's kind of how they would like to ask that question. So let's do a proof on that. How fast is the moon going? So when we want to figure out how fast the moon is going, remember we can just put it into this equation. The v of the moon is going to be equal to the square root of g. I'm going to write it right here. No, I'll write here, whatever. G times the mass of the Earth. I'll put a little e there just so you know that's the mass of the Earth. Remember, the mass of the satellite doesn't matter. That's the weird thing about it, right? It's not the weird thing, it's physics. The mass of the satellite doesn't matter. What does matter is the mass of the massive object that they are orbiting around. So divided by the radius. And so in this case, the velocity of the moon is going to be equal to, and I'm not going to write out g. G is 6.67 times 10 to the negative 11th. But the mass of the Earth is 6e24, and that's 6 times 10 to the 24th, right? And the radius all the way out there, what was that? That was 3.9 E8. 3.9 E8. And if you do this in your calculator, you get about 1012.99 meters per second. Okay, now we do the same thing for the moon. So I do the same thing for the moon, and I get the v of the moon is equal to g times the mass of the moon. I have it written down here somewhere. Is the mass of the moon is... Oh, sorry. It's not the mass of the moon, is it? It's the mass of the Earth, 6e24, divided by the radius this time is going to be half of the radius of before. Yeah, okay, so now I'm back on track. Half of 3.9 E8. And if you do that, you end up getting 1,432.59 meters per second. Now, if you take 1,000, and this is my proof, 1,432.59, and you divide it by 1,012.99, guess what you get? You end up getting 1.41 times, right, the velocity of the moon. So this is basically saying and basically proving that Kepler was right when he said those ratios are correct. So this is actually a very simple ratio, which I really want to point out to you, that right there, that for any velocity, for any satellite inside of a system, then the ratio will be the same for all of them. So in a place like Saturn, or a planet like Jupiter, which has something like 20, 30 satellites, 20 or 30 moons, if you will, every one of them follows the same ratio. And the ratio would be the velocity squared times the radius of one would be the same ratio as the velocity squared times the radius of the other. And so that's a very typical question that they would ask you on an AP exam. And so let's give that a try on some of the Sparky quiz questions. Alrighty? Okay. So have at it. If I can find where my mouse went. There we go. And I'm almost out of here.